The fundamental theorem of calculus at first might show us something that we think is pretty obvious, but really what it does is it shows the relationship between the two main parts of calculus, which are derivatives and integrals. So if you look at this expression here, it looks sort of complicated, but really all it's saying is if you take the integral of a function between two values, and then you take the derivative of that, you essentially get the function back. So in other words, the derivative and the integral basically cancel out with each other. In fact, they act as the inverses of each other. One does something, the other one undoes that thing. So that's essentially all the fundamental theorem of calculus tells us. It tells us that the derivative and the integral are inverses of each other. Now, this only applies when the function is continuous between our starting and our ending points for these intervals. Okay? So that's the first one here is, sometimes called the first fundamental theorem of calculus. The second fundamental theorem of calculus has to do with evaluating an integral. And it's basically, what it basically says is to evaluate an integral, we do the integral evaluated at b, or the final point in our interval, minus at a. And this is what we use to determine areas and stuff like that. So just some common notation here. Usually what we say, what we do is we call capital F is a function of x. That's the integral of lowercase f. So like for example, ft dt. So capital F just refers to the integral of f. Okay, just like f prime would be the derivative of f, right? Capital F refers to the integral. So that's what we mean here when we say this capital F evaluated at b minus the capital F evaluated at a is just this integral evaluated at b and a. So that's just some notation. So let's verify this with an example. In this question, we're asked to take the derivative with respect to x of this function right here. And that you notice this function right here is an integral, right? So we're essentially asked to take the derivative of the integral. So without using our first fundamental theorem of calculus, let's just try to evaluate this sort of blindly, right? So for example, let's try to do the integral first and then apply the derivative to it and see what happens. So we'll start with taking the antiderivative of, so we'll say d over dx. Let's just d by dx. Let's just leave that there and let's do this integral. So the integral here is, the antiderivative here is 1/3 t cubed minus t squared, plus 3t. Okay, we should be comfortable about taking that antiderivative. And then we're evaluating it between 4 and x, right? X is, some point along, it's some generic point along there. So let's evaluate it. So all we're doing is we're basically plugging x and 4 into that equation and subtracting them using the second fundamental theorem of calculus, right? So this ends up being d by dx. So that thing evaluated at x is going to be 1/3 x cubed minus x squared plus 3x, right? All subtracting that thing evaluated at 4, which ends up being 52/3 if you do the calculation there. So if we do that, we now have an expression with x in it, and the next step is to take the derivative of it, because that's what the question asks for us for. It wants the derivative of the integral. So if we take the derivative of it, what are we going to get? Well, let's just do it one step at a time. So the first part is we move the 3 down, we subtract 1, it's just going to be x squared. The second part, we're going to move that 2 down, 2x. The third part, which just becomes 3. And that 52/3 disappears, right? So it evaluates to this, right? This is our final answer. Now, what do you notice? Isn't it just this, but with x's instead of t's, right? So remember, that's what our fundamental theorem of calculus states, right? It states that the derivative of an integral is the function itself. Okay? The variable might change because we plugged in that variable of x, but, the function is itself, as long as it's continuous between, 4 and x. And we know that this function is continuous everywhere. Okay? So instead of doing all this work, if you got a problem like this, you could literally just evaluate it, right? You could just say, oh, I know that this equals 2x squared plus 2x plus 3. That's it. That's the answer, right? And the other thing to notice is the starting point of the interval, the 4, doesn't come into play at all. Because when you take the derivative of the integral, that part is going to be constant, right? So it's always going to disappear. So it actually doesn't matter what this is as long as the function is continuous between 4 and x, okay? So this is what I want to see you do. You don't have to do all this work to prove it each time. And sometimes it'll give you things that we don't even know how to find the derivative of. So for this next example, how could we evaluate this without having to take the integral? Because you might think, okay, we need to take the integral first and then take the derivative. But we can do the same thing, right? So in other words, so like this, instead of our x, now we have a number here, right? So basically that we can consider that our x, right? If in fact we substitute in for x, we can then plug in the x over the pi over 4 later, right? So I want you to try to evaluate this yourself. Pause the video here, try it yourself, unpause, and we'll quickly go through the answer. So you should see that this evaluates to, we're just replacing that t, we'll call it with x first. So sine x cos x, right? Because we're plugging in the x instead of the t's, right? And these two things, the integral and the derivative, basically cancel out. So if we want to evaluate that at pi over 4, all we need to do is plug in pi over 4. So sine pi over 4, cos pi over 4, and those both evaluate to 1 over root 2, right? It's 1 over root 2 times 1 over root 2, which just gives us 1 over 2. Did you see that? So again, we didn't have to use this 0 at all as long as the function is continuous between these two. And we know sine t is continuous, cos t is continuous, so multiplied together, they are also going to be continuous. Okay, last example. This one is a tiny bit more complicated. We have, instead of evaluating between a number and another number or just an x, we actually have a function that we're going to plug into this. And remember, really what we're doing is we're plugging the function in for all the t's in here, right? Because t is our variable of integration. So we might just, think we can blindly plug in this 2 times x squared minus 1, x squared squared plus 2. But we have to be a little bit careful. Because remember, we can consider this function, just this part of it, 2t minus 1 over t squared plus 2 dt. We can consider this part of it a function f of x, right? That's the integral. We always use the capital F for that. So this part of the function is f of x. So we can rewrite this expression as d by dx of f of x, right? So in other words, another way of writing this, you might remember, is just f prime of x, right? We're just taking the derivative of the integral, right? Now, remember what we're plugging in. We're not actually plugging in x. We're plugging in a function, x squared. So this function actually, let's call it g of x, for example. So we're not actually plugging in f at x. We're plugging in a function. Let me erase that. We're plugging in a function, g of x, right? We're plugging in a function, erase again. We're plugging in a function g of x. So when you take the derivative of this, something should trigger in your mind. Shouldn't we use the chain rule? Shouldn't this be f prime of g of x times g prime of x? And in fact, that's what we have to do. So this, because you have a function in the upper bound, you actually have to multiply your answer by the derivative of the upper bound. So what you're going to get, our final answer to this, is going to be, well, just this function, but we plug in the x squared, and then we have to multiply by the derivative at the end. So it's going to be 2x squared minus 1 over x to the 4 plus 2 times the derivative of x squared, which is just 2x. That's it. Of course, we could expand and simplify that and whatever, but that's essentially what it evaluates to. So the one thing to keep in mind when we have the first fundamental theorem of calculus, when the x up here is a function, you have to multiply by the derivative of that at the end because of the chain rule. So there's sort of like a star, an asterisk goes with that. When you have d by dx between a and a function, we'll call it g of x, of f of t dt, that's going to be f of g of x times g prime of x, right? So we're going to plug it in and then multiply with the derivative. So this is like sort of the caveat if the upper bound is a function, okay? And once again, the lower bound doesn't matter as long as the function is continuous. And just to check, this function is continuous because the denominator will never be 0.